All right. So welcome everyone to our October vast. Snuck up on us that it's already fall. We have two talks today, both sort of on the theme of blowing stars up, which is near and dear to my heart. Before I introduce those talks, I just want to tell you about what's coming up. In November, we're going to have several talks, shorter than normal, so we can have a few of them, talks on alert brokers, which I know nothing about, but I guess, how you find out that something's happening in the sky. And so we'll hear from several of them. And in December, our tradition in the making is that we do lightning talks. So short talks where you can describe some software that might be new and maybe you want people in the astro community to know about. A great venue for students as well to talk about some of your software projects. And we aim to do 6 lightning talks in December to wrap up the calendar year. If you're interested in giving one of those lightning talks, you can go to our GitHub page. You can file an issue that you want to give a talk, and you can even mark it as a lightning talk, and we will find you. All right. So with that said, we're going to get started on today's talks. We have 2 talks. Both are from graduating or soon to be defending grad students, meaning both are on the job market. So pay close attention, and maybe you can have a new colleague if you're looking. We're going to start with Sam Dunham. Sam is actually recently joined us this year as one of the VAST organizers. We're not playing favorites. He had gone through the filing of an issue to give a talk before we recruited him as an organizer. So it's all on the up and up. And Sam is going to talk to us about Thornado, a code that he's been developing with colleagues at Oak Ridge. Sam's at Vanderbilt, but I think spends most of his time at Oak Ridge. So we'll turn things over to Sam. You should be able to share.
All right, sounds good. Yeah, thank you. There's a chat already. That's different, okay. Yes. So thanks for the introduction. Yeah, and thanks to the other organizers for accepting my proposal to talk to you about Thornado Hydro, XCFC, which has comprised the bulk of my dissertation work. So Thornado is a red hydro code, and the authors listed here have mostly worked on the hydro part. So Brandon Barker, who's going to talk next, he worked a lot on the non-relativistic hydro solver with a tabulated nuclear equation of state, but he's going to talk about a different code that also blows up stars. Jesse Buffalo worked a lot on the non-relativistic hydro solver for the ideal equation of state, and is now working on implementing GR-MHD to the code. That's me. Zach Elledge is actually working on the GR neutrino transport, which is not hydro, but I think he's graduating in May of 24, so just helping get his name out there a little bit. Eirik Endeve is the architect of the whole thing. Tony Mezzacappa is a professor at UT, and he also has lots of input on code development. David Pochik worked on the non-relativistic hydro with a tabulated equation of state also, but he focused on implementing a bound enforcing limiter, which I'm not going to talk about, but there's a whole paper on it if you're interested in details. And Nick Roberts also doesn't work on Thornado directly, but he works on his own code, Poseidon, which is a gravity solver that uses the same approximation to GR that Thornado uses, and his gravity solver is the one that Thornado uses. So here is the URL to the GitHub page for Thornado and a QR code that will take you there also. And here's a URL to my website and a QR code that will take you there, which I don't normally include on my talks, but like Mike said, I'm on the job market. So maybe if you see my name on an application, hopefully it will trigger a good memory. But I guess that depends on how this talk goes. Oh, okay. So the toolkit for high order neutrino radiation hydrodynamics. That's the acronym for Thornado. And it's the red hydro code, like I mentioned, whose primary focus right now is going to be simulating core collapse supernovae using high order discontinuous Galerkin methods, or DG methods for short. It uses explicit Runge-Kutta time stepping for the pure hydro problems, and then IMAX methods for the transport. It uses an approximation to GR, which is an improvement on what a lot of production codes right now use for supernovae, which is they modify the monopole term for the Newtonian potential with GR corrections. And so this is this formulation that we use is consistent with the Einstein equations, which is nice. We use the Valencia formulation of the hydro equations. We have a spectral two-moment model with an analytic M1 closure for the transport, interfaces to weak lib, and the ability to interface with other equations of state and opacity tables and such. We get self-gravity via Poseidon, which I mentioned, so a coupling to Poseidon. Thornado can run on GPUs via OpenACC or OpenMP pragmas, which is critical for current generation supercomputers and also future generation supercomputers for which GPUs, it looks like, are going to be the main focus of those machines. And Thornado is also in the process of being coupled to AMRX, which is a nice software framework that provides application codes the ability to run in parallel with MPI and also make use of block structured adaptive mesh refinement. And all the codes mentioned on here, all the links, and also Thornado are all publicly available and open source, as most codes should be, at least for science. Okay, so one slide on the 3+1 decomposition, which is it's part of the physical model that the code is based on. And so this block here is supposed to represent space-time, and each point on here, each point in this block is an event in space-time. And space-time doesn't evolve, really, but as people who are modeling something, we like to think of it as specifying initial conditions and then evolving those initial conditions in time according to the hydro equations or the Einstein equations or the coupled versions of those two. And so this red squiggly line here is meant to represent a spatial hypersurface at some time t. And then a small amount of time later, this hypersurface has evolved to the blue hypersurface at time t plus dt. And the gamma ij is the restriction of the metric, which exists everywhere. It's the restriction of the metric to that hypersurface. And mathematically, it's the pullback of the metric under these embedding maps, which I won't talk about because it's not so important, but I just wanted to define what these gamma ij's are, point out that they depend on time. And another thing here that I want to emphasize is alpha, which is the lapse function. That so when you do this 3+1 decomposition, the full metric, you end up with 4 degrees of freedom, which are the lapse function, and 3 components of the shift vector. And the lapse function in the Newtonian limit, the lapse function alpha is equal to 1 plus phi, where phi is the Newtonian gravitational potential. And so whenever you see alpha, you can sort of think of it as the gravitational potential. And I think that's everything I wanted to say for this slide. Okay, so Thornado doesn't solve that. Sorry, we make an approximation that's the conformally flat condition, where the 3 metric, which depends on points in space-time, is written as a scalar function that depends on space-time, multiplied by a time-independent flat space metric that only depends on space. And so as far as the 3 metric is concerned, the effects of GR are entirely encapsulated within this scalar function. And some additional approximations that go in are the trace of the extrinsic curvature and its time derivative are 0, always and everywhere. And I'm not going to talk about this much, but if you have questions about it, I can try to talk a little bit about what this K is. But it's not so important for the hydro for this talk, so I don't emphasize it here. Some features of this approximation are that it is exact in spherical symmetry. And that's really nice because one thing that means is that if you run 1D core collapse simulations, from which a lot of science can still be gleaned, then you're not making an approximation to GR, you're doing full GR. And it's been shown that even in multi-dimensional simulations, this approximation is appropriate for solely rotating progenitors, which a lot of supernovae are. Another consequence of this condition is that it transforms the hyperbolic Einstein equations into a system of elliptic equations. And so you can solve the equation at each time, the system of equations at each time, and you can, by doing so, enforce the constraints that are imposed by the Einstein equations. And one advantage of that is that it's good for long time simulations. So if you want to do simulations of order seconds or longer even, the enforcing these constraints can give you some stability. And that's in contrast to free evolution schemes like BSSN, where you don't enforce the constraints, but you monitor them and just make sure that they don't exceed a certain threshold. So, excuse me, a special case of this is the Schwarzschild spacetime in isotropic coordinates. The Schwarzschild spacetime you may be familiar with. It's just the spacetime around a non-rotating, spherically symmetric compact object of mass m, like a black hole. And this is just to show you what these functions can look like in a simple case. And all that I will say about these really is that as the radial coordinate is much, much larger than the Schwarzschild radius, these alpha and lapse functions approach 1, which is what you expect, because if you're very far away, then spacetime is approximately flat, and alpha and psi equal to 1 is the flat space limit. So just to show that. Okay, so a little bit about the DG method. The DG method starts by breaking up your computational domain into a series of non-overlapping elements. And within each element, you approximate the solution as a polynomial. And so this cartoon is meant to represent one element, where the true solution is this black curve. And these colored lines are polynomials of increasing degree. And so by changing this parameter n, which is the number of points that you use, you can think of it as the degree of the polynomial plus 1 or minus 1 or something. You just change this parameter at the beginning of your run, and you immediately get higher order polynomials in all of your elements. And what's nice about this is that you don't have to change the code. That's one nice thing. And another nice thing is that you could get high degree polynomials without increasing the width of your stencil. So if you wanted a degree 50 polynomial for some reason, then you still would only need to communicate with the nearest neighbors of your current element. And that has advantages for scaling on large heterogeneous architectures like GPUs and multiple CPUs. Like finite volume methods can also do high order polynomials, but you have to increase the stencil the higher degree you want, and that can hurt some scalability. Okay. Right. So if you have a smooth problem, like I just showed, a smooth profile, you can check the error of your code or how well you're doing. And the way we do that can be shown here. So this is a sine wave in density. And what's going to happen is that this just advects across the domain with periodic boundaries. And after one period, it ends up right back where it started. And so if you take the difference in the final solution minus the initial, if your code were perfect, you would get 0, but you don't get 0, you get some error that depends on your scheme and it depends on your resolution. And so for here, what we did is run a bunch of these problems where we increased the number of elements. And what you can see is that as you increase the number of elements, your error goes down, which is what you expect. And what you also see is that if you use third order methods, which are the red dots, then your error goes down at a faster rate. And it goes down with roughly parallel to this red line, which is proportional to the mesh size cubed. And this blue line is proportional to the mesh size squared. And so this plot just shows that you get the solution you expect, and you get the rate of convergence to the correct solution that you expect. But what you can also see is that if you wanted an error of, say, 10 to the minus 7, if you use third order methods, you need about 500 degrees of freedom, which is in some sense proportional to the number of flops that you have to do when you do your simulations. But if you use second order methods and you want that same error, then you need about 1,000 degrees of freedom. And so if you want to make the best use of your computational resources, which are often limited, then using a higher order method is advantageous. Okay, or don't advance, that's fine. Okay, so that was a smooth problem. The nice thing, or the problem with fluid equations, depending on your point of view, is they can develop discontinuities. And if you try to approximate a discontinuity with a higher order polynomial, then you get non-physical oscillations. And so in order to mitigate those, DG methods require some kind of a slope limiter. And for Thornado, we use a simple, it's called the min-mod limiter. And I won't go into detail, but basically what it does is you start out with your high degree polynomial, which now I've expressed in the basis of Legendre polynomials, which are hierarchical in the sense that piece of 1 is a constant, piece of 2 is linear, piece of 3 is quadratic, and so forth. And you take that higher order polynomial and you replace it with a truncated polynomial that only has a constant term and a linear term. And so by doing that, you remove all of the oscillations. And the linear coefficient is modified, but the constant coefficient is not modified. And that's important because that means that if you apply this limiter and you care about conserving things, like if you want to conserve mass in your code, this limiter will not affect that. You'll still conserve mass to the same degree, which is nice. So I'm going to talk about some applications. So Thornado has been used to investigate the role of GR on the SASE, which is a hydrodynamic instability that is observed in core collapse supernova simulations. It looks roughly like this figure on the left, where you have this shocked fluid in the dark purple, and it sort of sloshes back and forth, and it gets the post-shock region gets larger and larger, and it just is unstable. And so what we did is with Thornado, we simulated this instability with non-relativistic hydro and Newtonian gravity, and that gives the blue line here. And then we did the same simulation with GR hydro and GR gravity, and that gives the orange line. All this was with Thornado. And so what we found, which was interesting, was that the non-relativistic runs leads to the SASE growing at a much faster rate, which was unexpected and interesting. And that paper is in the process. We're addressing referee comments right now, but hopefully it will be published soon next year. And I forgot my clock, so I don't know what time it is, but I think I'm doing good. Okay.
You
so
have 5 minutes.
Okay, perfect. Thank you. So I mentioned that the code has been coupled to AMRX, and this is an example of that. So this is the density field from a Kelvin-Humboldt's instability problem, where the refinement criteria is based on the gradient of the density. And so you can see that you get more grid points where you have a higher density gradient. And just to prove that I'm not, that it is really adaptive, this is a movie, a simulation. Just fun to watch. These movies are great. Also, hydro is great. It's all great. Okay, cool. Where'd it go? Okay, so that showed that Thornado was coupled to AMRX, and this figure demonstrates its coupling to AMRX and to Poseidon, which is the gravity solver. So here we simulated the collapse of a realistic progenitor. It was a 15 solar mass star. And we simulated the collapse of the core, I guess, with mesh refinement. And so these blue lines denote the mesh refinement boundaries. For this problem, they're not adaptive. They're just fixed at these radii. And the different colors correspond to central densities hitting various decades. And this was just to show really that it collapses like you would expect. There are no sort of spurious features at the refinement boundaries, which we had for months, but they're finally gone. So I'm happy to show this figure. And the other nice thing to see is that in the bottom left panel, solid lines are the conformal factor and the dashed lines are the lapse function. And as this thing collapses and the central portion compactifies, it sort of becomes more relativistic in some sense. And so the degree by which these two quantities deviate from one is a measure of the degree of relativity of the system, which is interesting to see. And so this thing collapses, and then eventually it hits the nuclear saturation density and bounces and creates a bounce shock that propagates outward. And we capture that phase also. And so this was the same problem, just at the post-bounce phase. And again, just to show that the shock propagates outward like you would expect, and there's no spurious features, which is very encouraging. And okay, I think I'm going to finish a little bit early, but that's okay. Here's a bibliography for people who are interested in such things. And so just to summarize, we can run pure hydro problems in GR with adaptive mesh refinement. And Thornado can do adiabatic collapse simulations with mesh refinement in full GR, because there's no approximation in 1D. And we're working to couple the transport in also to do do full-on core collapse simulations. And those are, I think they're in progress right now. I think Zach is actually doing a run that couples all the physics together and will be a real simulation. So that's all very exciting. And yeah, so yes, I'll thank you all for your time and your attention, and happy to take any questions.
Great, thank you, Sam. I forgot to mention it ahead of time. If you have questions, drop them in the chat. We'll do a quick question now, and then we'll have more extended time for questions after both talks. Since I forgot to mention that, and I don't see any questions here, Sam, I'll ask you one. So you showed two different convergence, one with second order, one with third order, and said it needs more elements to get the same accuracy. What's the practical limit on how high of an order you can go to? I mean, why not just go 1,000 order with one element, right?
Yeah, good point. Well, so one thing I think is that you would, if you want to capture discontinuities, then regardless of the degree of the polynomial, I think you would have trouble doing that with one element.
Right. Yeah.
But yeah, I mean, you could do, degree 4, 5, or 6. I think you would always need more elements. I'm not sure if there is. So eventually, when you get to very high degrees, you can get these things called aliasing errors.
Sure.
That's a term that I've seen. I'm not sure what it means, but it happens when you get high order polynomials. And one reason that we don't go to super high order is that our slope limiter right now is not so sophisticated. And so even if we had a 1,000-degree polynomial, after the limiter was applied, it would only be linear. And so you would lose all of that accuracy. But
so what order do you normally run in?
Usually we run with second or third order methods. Okay. We are working on implementing slope limiters that can retain more higher order accuracy. They're usually based on Wino methods and things like that, but they have not been fully tested or implemented in the code yet.
Okay, cool. All right, we'll move on. Next up is Brandon Barker. Brandon's coming from MSU and Los Alamos, also graduating and also on the job market, and has perhaps the most fun acronym for his code, I think. I mean, Sam, your acronym worked very hard as well, but I think Brandon wins the acronym game. So Brandon, you should be able to share.
Yes, I wish I could take credit for the acronym. I do, but it was not me. Can you see everything fine, Mike?
Yep, looks great. Right.
So, thank you. So, quick introduction. This is my cat. He might have some things to say, but they're not that important. So I'm Brandon. I am a graduate fellow at Michigan State University and Los Alamos National Lab, 50-50-ish. Conveniently spending my winters in New Mexico and my summers in Michigan now. So I'm going to talk a bit about Phoebus, the code I've been working on lately in development at Los Alamos National Lab, which is the best acronym I've ever seen. Is PH51 Ergs blows up stars. And complementary, but different from Sam's talk, I'll be talking a little bit more about software design than the numerical methods in Phoebus. So to start off a little bit, I want to step back. We're interested, in problems of relativistic astrophysics. These might be things like supernovae, near and dear to me, things that blow up, things that are general relativistic, things that are extreme in space. And these are complex, multi-scale, multi-physics problems. So in a given problem, like a supernova, we need to capture things like general relativity, neutrino transport, or photon transport, depending on which part of the supernova you're talking about. There's a whole host of complicated microphysics, from neutrino matter coupling, photon line opacities, nuclear reaction rates, nuclear equation of state of a neutron star, and these sorts of things, and down to everyone's favorite of magnetic fields that are everywhere that we have to take care of somehow. And so these represent in some way all of the four forces of nature, and these are coupled across many spatial and temporal scales. And depending on the problem, we may need to try to resolve turbulent dissipation scales, the magnetorotational instability we'll talk about a little bit later, all the way up to maybe stellar radiuses or accretion disk scales, things like this. And these operate on something like the central engines might be milliseconds or hundreds of milliseconds to seconds, but with observable timescales that span out days to months. And this is made even more complicated by the fact that on these different spatial and temporal scales, the physics that we need may change. So in a supernova, we need really good neutrino transport for the first few seconds, but not on the 24-hour timescales of shock breakout. And so the needs evolve with space and time as well, which makes things both exciting and complicated. And so this is to say that all of these problems that we're interested in are massive computational challenges. And our progress in these fields here for supernovae, but in general, has progressed with advances in our computational power. So we get better supercomputers, we get better simulations that run longer, or we include more physics or something like this. And the astute observer might notice that this slide is a little bit dated, not just because the citations are a few years old, but 500 petaflops is now old news, reaching exascale architectures. And that is both exciting and part of the problem. Scientific advances follow these leaps in computational power, but we're getting to the point that we're going to require ever more sophisticated software in order to make use of that computational power, right? This is why we are not using the same codes that we used a decade or 2 decades ago. We need something that is more sophisticated, that can work on a heterogeneous architecture and take advantage of GPUs or whatever architecture might come next that outdoes a GPU, right? And so that is sort of where Phoebus and Thornado and AMRX, like Sam talked about, and other things come into the picture, in that we need to put all of this physics in a way that is, from a software design perspective, smart and can be efficient on these different architectures. And so that's where Phoebus comes in. Phoebus is in development mainly at Los Alamos National Lab. And despite that, it is fully open source. There are no strings attached to that. It's on GitHub right now. The list of collaborators are here, largely LANL affiliations, but slowly expanding. And we very much welcome new collaborators. We're very excited. Phoebus is close to be up and running, and we welcome people who have new ideas to put in. And so what is Phoebus? Phoebus is developed, like I mentioned, for problems in relativistic astrophysics with a software design perspective that wants to take use of these heterogeneous architectures. We have will have general relativistic radiation magnetohydrodynamics. We use the Valencia formulation of GR hydro, like Sam mentioned. Radiation transport is included both for neutrinos and for photon radiation transport, with a few different methods like moment methods, a parameterized neutrino transport scheme that I'll mention a bit later, Monte Carlo transport, and these things, MHD with constrained transport, and GR. Similar, a few implementations of GR. We have analytic spacetimes like we might use for black hole accretion that has horizon penetrating coordinates and these things taken from that community. Also a spherically symmetric monopolar solver that is different from what Sam talked about with the conformally flat stuff, but is still very well suited to nearly spherically symmetric problems like multi-D supernovae. That is very exciting, that I look forward to seeing in action. And this is performance portable, and it has block structured adaptive mesh refinement. I'll talk about that a little bit more later, but it's developed right now for things like core clump supernovae, black hole accretion, binary mergers, but it's certainly not limited to these things. We can imagine your science application going here. We're very excited to start working with people on doing whatever science excites them. We've talked amongst ourselves a little bit about opportunities for X-ray bursts and things like this because of the wide range of spatial and temporal scales that Phoebus is able to handle. So Phoebus does not exist in a vacuum. Like Sam talked about, before, Thornado takes use of AMRX and all these other things. Phoebus has to as well. At the first level, Phoebus is built on Parthenon. Parthenon is our block-structured adaptive mesh refinement framework that provides data and loop abstractions, as well as a tasking model for downstream codes. It plays the same role for us as AMRX would in Thornado. So it handles our data, it handles the MPI structure, our data structures are all there in Parthenon. And that Parthenon was inspired heavily / split off from Athena++ developments. And so it is structured very similar to that. The microphysics in Phoebus are supported by what we call singularity EOS and singularity opacity. These are both open source as well, that provide GPU-friendly routines for equation of state and opacities. Singularity EOS is very widely used at the lab now. It has something like 10 plus equations of state spanning from astrophysical nuclear equations of state and the Helmholtz-Zeller equation of state off to some materials equations of state that boggle the astronomer's mind because they include solids, which shouldn't exist. Those are supported by Spiner, which is our library for data structures and table interpolation. And then at the bottom of all this, which is what we're going to spend some time talking about, is Cocos. Cocos is our a hardware agnostic library for performance portability. So instead of writing some like Pragma OMP parallel 4 or something, we write our loops as Cocos kernels, which are quite easy to write and read. And at compile time, Cocos specializes those kernels into the relevant code. And so this is to say that Phoebus is built on a large open source ecosystem with performance portability at its core. What do I mean by performance portability? This means sort of two things. It means one, portability. We want to go onto a different architecture. This might be a CPU GPU machine. It might be Okami or Fugaku that has these ARM CPUs that are weird or whatever, and we want to, at a bare minimum, be able to compile and run our code out of the box. But we also need performance on those architectures. And so Cocos provides support for this by allowing us to select at compile time what architecture we want to compile for, and then it specializes the relevant code. What this gives us is minimal code duplication and rewriting. We don't need different versions of our kernel that support CUDA or support HIP or whatever. We don't need preprocessor directives that switch out bits of code. It's one kernel, and then at compile time, CUDA or Cocos does whatever we need it to do. Performance portability is easier said than done. So these are a couple of timing plots with one side is GPU and one side is CPU. And what you need to take from this is that each line is a different loop pattern, a different way to access the data in a loop. And these loop patterns are provided by Cocos, and the plot is timing for different pieces of physics. So maybe the Riemann solver, constrained transport, and such things. And what you take away is that what is performant on a CPU is not performant on a GPU. That is that these two hardwares have very different needs when it comes to algorithm design. And we don't want to have to rewrite our code when we go to a different machine. We don't want to rewrite the loop structure. Cocos provides support for this by allowing us to switch out automatically the loop structure very easily on different architectures, play with it, see what works, what doesn't, without having to rewrite that code, which is exciting. There's a few other things that are difficult. Load imbalance is always a problem. Parthenon exposes this tasking framework, which exposes or expresses your physics in this sort of task tree where you have, thing A depends on B and C, and it resolves this whole task tree into what things can be done simultaneously and what things cannot be done simultaneously, what depends on what. And in Parthenon, these tasks operate on mesh blocks, which are discrete pieces of our mesh. If you're familiar with Athena, that language will sound familiar because it is the same. The issue with this is that when we want to launch a kernel, maybe one of these tasks, every kernel we launch imposes a latency when we go to the GPU. And that can really kill your performance. And so we have to deal with that somehow. And the way we deal with that in Parthenon and Phoebus is by coalescing these kernels together across multiple mesh blocks. And so we may take cheaper kernels that are not very computationally intensive, pack them all together and send them off to the GPU all at once. That way, instead of imposing n launch latencies, we get one launch latency, for example. And importantly, the way that these kernels get packed together, how packed, to what efficiency they're packed, and such things, is all runtime tunable. There's just some switches in your input deck, your input file, that lets you change this up and see how performant is it on your given architecture. So how does Phoebus and Parthenon perform? We're looking now at some scaling plots. We can just look at the top scaling plot. It's a weak scaling efficiency, where flat line means perfect scaling as a function of the number of nodes for various computers out there. And we'll notice a few things. For most of these computing architectures, the scaling is very good. I think on a simplified problem, we had like 90% weak scaling efficiency on almost 10,000 frontier nodes. And so it performs really well. And something else to notice is that there's two clustering of lines here. The top cluster of lines is GPU performance. The bottom cluster is CPU machines. And there's about an order of magnitude increase in performance by going from the CPU to the GPU, which is very exciting for us. So that we're really able to leverage all of these different machines efficiently without having to rewrite code for all of them or do anything like this. So what are we looking to do with Phoebus? What I've been developing it for and have interest in is collapsars. So these are accretion disks inside of massive, rapidly rotating stars, where instead of forming a neutron star and getting this neutrino-driven explosion and all this nice stuff that we love, we form a black hole, and the infalling stellar material circularizes into an accretion disk, and you get these jet outflows. These are interesting because they're believed to be the central engines of long gamma ray bursts and are possible R-process nucleosynthesis, which is what I'm most interested in for this problem. The movie here is a simplified setup. So it's an accretion disk. We're looking at the density. There's a black hole in the center that we're able to resolve the event horizon of on the grid. And then we get these jet outflows along the axis here. And it's very exciting. There's no neutrino transport in this, but it's got nuclear equation of state and magnetic fields and all the other bells and whistles. Soon we'll be doing this with all of the bells and whistles, including energy-dependent Monte Carlo neutrino transport and improved initial conditions, meaning that we follow the circularization of the infalling stellar material and the formation of that accretion disk and the jets. That's important because a lot of studies these days will initialize an accretion disk around a black hole and use that as a surrogate for the collapsar, but it doesn't include all the physics like feedback of the infalling stellar material on the disk and these things. So very exciting stuff coming soon. There are supernova runs happening with simplified neutrino transport. So this is a set of 1D runs with parametrized neutrino transport, where we can just tune up the neutrino luminosity and artificially drive an explosion. So that's all ready, and 3D tests to make sure that all of that is coupled together are probably in progress right now if the supercomputer will ever put our jobs through. And soon we'll be doing this with energy-dependent transport as well, not parameterized light bulb transport. There's already production quality runs happening with Phoebus. Ben Ryan is doing this for photon radiation supported black hole accretion disks. These are accretion disks inside of a supermassive black hole accretion disk, I believe is the science setting that he's doing here. And these are some of the longest running in physical time simulations to date. And so they're very exciting, and those are in progress already. So a few things that are coming soon with Phoebus. I mentioned the 3D GR MHD black hole accretion models and the collapsar simulations with our process yields. Hoping to get those collapsar simulations started by the end of the year. There's a couple of roadblocks in the way. And then 3D core collapse supernova simulations with energy-dependent neutrino transport and real GR, hopefully coming in the next year or so. someone's postdoc fellowship proposals depend on that, so that will be implemented. We'll be implementing higher fidelity neutrino transport, this sort of moment method with a exact Monte Carlo closure on top of it that carries the energy and angular information in a more accurate way. And then a nuclear network to run inline to help support some of these other science goals. I'll put up my summary. I've introduced Phoebus. This is a code to model broadly phenomena in relativistic astrophysics. At the heart of Phoebus is performance portability, and that is something that's very difficult to achieve, and that requires tuning the algorithm to the hardware. And as much as we would like to, we can't control the hardware. And there's been huge wins for us by exposing these tuning parameters at runtime using Cocos that allows us to tune out the loop abstractions, the loop patterns, and these sorts of things all at runtime to tune every aspect of the simulation. It's already at production capability for some problems. Very soon we'll be doing some very exciting full physics simulations with Phoebus as well. All of the relevant GitHub links for everything I talked about are here on the left, and I will end for questions.
Awesome. Another nice talk. Thank you. Thank you, Brandon. I only saw it mentioned at the end, nuclear reaction networks.
Yes, they're not in at all right now. It's just a longer.
What's your plan for that? As you know, I have quite an interest.
Yes, so we need it running in line. Probably talk with you sooner or later to leverage PyNucastro to get some of that stuff written up. In terms of implementation, Parthenon supports these sparse on block buzzword variables that allows us to implement isotopics in a very efficient way, so that we're only evolving and storing what we need to where we need to on the grid. And so that's part of the plan for that. And hopefully that should be quite efficient.
Okay, nice. All right, two excellent talks by two soon-to-be doctors on the job market. Let's open things up for questions. If you have questions for either Brandon or Sam, please drop a note in the chat. And I think we're going to turn things over to Emerita, who will take the lead on questions. And I have more questions too, but I'd like to give our chat the first dibs.
Okay.
You're a little low. You're low.
Yeah.
Oh, there you go.
Hi, thank you. Okay, so let's start with the questions. Please post them in the chat or raise your hand, and I'll be monitoring both of them. While we're waiting for questions coming in from people, I would like to break the ice a bit and start asking questions myself. So, Brandon, I have a quick question for you. For the black hole simulations that are being done, is the disk being constantly fed, or in case of like where you're looking at physical timescales?
In terms of Ben Ryan and stuff, I don't actually know. I don't think his disks are being continuously. I would think they should be.
Yeah.
I don't know. If they're in a larger accretion disk, maybe they should be. But I don't actually know what Ben Ryan's doing. The ones that I'm going to be running soon, they will be continuously fed by the infalling stellar material.
Yeah, that's
Those
what I
will
was
be
wondering. Yeah.
those will be continuously fed. We'll be setting up a parametrized star, but a star, and allowing that to infall and circularize, and we'll keep all of that.
Cool, thanks. Okay. Okay. So there's a question from Jess for Brandon. Do the 1D CCSM core collapse supernova models include approximations for multidimensional GRMH defects?
No, it's strictly, those are strict spherical symmetry. I assume you're thinking of something like including convection or turbulence parametrized in 1D. No, there's none of that in Phoebus at the moment.
Okay.
Which is why we needed an artificially driven explosion.
Thank you, Brandon. Michael, would you like to ask the question that you had?
Yeah. I know a bit more about how Brandon's doing GPU stuff because it's very similar to what we do with the offloader. But Sam, you said you're using OpenMP and OpenACC. Can you maybe say where you're using one versus the other and which is better supported?
Yeah, I may have misspoke. So it's not one. So we either use one or the other everywhere for the simulation. Yeah. I don't know about better supported. So I prefer OpenACC because I've had better luck with the compiler. I know for a while the Intel compiler, it would take like an hour to compile long modules for some reason. But with the what's the other one? It's been a while. Anyway, yeah. So OpenACC it compiled faster, but that was a hardware issue, not a OpenACC thing. And yeah, we apply the pragmas around. Well, it's around the whole code, but it mostly around nested do loops or nested do loops. We'll have pragmas that it'll be either OpenACC or OpenMP offloading or just OpenMP if you're not on a big machine like that.
Does the OpenACC work on Frontier?
I've never used Frontier. I think it does because I'm pretty sure I think Austin is doing some simulations with Flash and Thornado, and it might be using Frontier, but I am not sure. I'm pretty sure Thornado does run on Frontier, but I'm not sure about what GPU method they're using.
Okay, cool. Thanks.
I think there is a comment from Joe Renaud or a question. This is the first I've heard about COCOS. Does using COCOS lead to performance overhead when it is just being used on a regular multi-core workstation?
No, the overhead from having COCOS handle things is minimal to zero. We use it for our CPU runs as well, and it works great.
Yeah. Okay. Great.
Oh, Eric answered. We use OpenMP on Frontier.
Okay.
All right. Do we have any other questions for either of our speakers? Oh, sorry, that's your role. I'm sorry.
No, that's totally fine.
It's all good.
Those are shared roles. It's a team, you know. Yeah.
If not, let's thank both Sam and Brandon again. Both are working on very complex codes, doing an awesome job, gave great talks. Let's do a reminder that next month we're doing alert brokers. We have a couple of talks lined up and we'll flesh out that schedule over the next month. And so we'll hear about how, well, I don't really know what an alert broker is, so I'm going to learn what an alert broker is. And then in December, we're doing lightning talks again. So if you want to share, 5 minutes about some cool project you've been working on, especially if you're a student, sign up, post an issue, and we'd love to hear from you.
Also student and on job market.
Yeah, and on the job market as well. Yeah. Absolutely. Yeah. All right, I'm going to stop the recording. Thank you both of you. I don't even know where to stop. Here.
Yeah. Thank you all for joining.
Thank you all.
Thanks.